Okay, thank you very much. And so I'll be talking about atomic physics and why it can contribute to neutrino and dark matter detections. And here are my collaborators, former master student Chen Wu, who is in the MIT PhD program now. Chen Wu is my PhD student, and we have a nuclear physicist, and also Chihang Liu and myself. And also we have Xinchang Ji and Kening Huang. They are experts in atomic physics, and we also have Henry Liu's group, Henry Wang's group, and Dennis Seneca. They are experimentalists. So why bother? We are interested in neutrino and dark matter physics because there are portals to new physics. So what is a portal according to N. Nelson? This is what a portal might look like. It is a gate that brings you from this world to another world. So you step from this side and you come up from some place completely different. And so in physics, that tells you that those particles can connect our standard model particles into new physics. Let me start with neutrinos. We all know that we are all familiar with this list. There are challenges and opportunities. For example, what are the absolute neutrino masses and what's the mass hierarchy, and also whether they are Dirac or Majorana neutrinos, and whether they are non-zero CP violating phase or phases, and also are there stereo neutrinos? That means that there are neutrinos. They don't couple to standard model. They don't couple to do standard model interactions, but they can mix with standard model neutrinos, of course, stereo neutrinos, and also whether neutrinos could have exotic electromagnetic properties like mini charge, magnetic moment, and so on. So there are those are all probes to new physics. For example, let's look at the neutrino magnetic moment. In standard model, neutrino, even though it's massless, it could have a non-zero magnetic moment through this type of interaction. So a neutrino can split into a charged lepton and W boson, so it has an electromagnetic cloud surrounding it. And when you couple this cloud through a photon, it can probe its magnetic moment. The standard model contribution of the magnetic moment gives this number. It's proportional to 1 power of neutrino mass, because this diagram requires flipping of the helicity or chirality. So you need to insert 1 power of mass. Suppose the mass is 1 eV, then the magnetic moment is 10 to the minus 19 of nuclear magneton. This is much smaller than the current experimental lower bound. So if one go ahead to do the experiment with the current sensitivity and measure something non-zero, then it clearly has to come from physics. So it's dark matter. Now we know that the dark matter density is much higher than the standard model particles. And so their existence might hint that there is a dark sector, not just one or two, not just a simple dark matter particles of one species. There could be lots of different particles and of different interactions in the so-called dark sector. And here are some portals between the dark sector and the standard model particles. You can start the construction from vector particle and the scalar, including pseudo-scalar and also fermions. And for the vector, one could construct a dark matter photon, and that will mix with the standard model gauge boson. And also the pseudo-scalar, you could look like an axion type of interaction to standard model fields, and also the scalar particles could couple to standard model Higgs. And also stereo neutrinos can mix with standard model neutrinos. There are other dark matter candidates, for example, measures that includes black holes and as dark matter candidates and also WIMP. And there are different ways of detect dark matters, and we are most interested in the so-called direct detection that involves scattering dark matter particles with standard model particles and look for the cross-section reactions, scattering reactions. So why atomic physics? Typically, when you think about atomic physics, you are thinking about scales of EV. While neutrino physics coming from reactant neutrinos involves typical nuclear physics scale of MeV. And dark matter candidates, when you think about WIMP, that comes from wind interaction scale, so it's way above GeV. So why are those scales sort of can come together? So, and it turns out a nice way to bring them together is at KeV, because from the neutrino magnetic moment study, as we will see later on, that the cross-section is much more enhanced when the energy transfer is small. It actually is proportional to 1 over energy transfer. So it makes sense to go to lower energy. And the current, the best resolution for the germanium detector, the threshold is around 0.1 keV. And for dark matter, because they are non-relativistic particles, if you assume that the dark matter has the relative velocity to the Earth as the CMB frame to the Earth, then their velocity relative to Earth is like 1,000th of the speed of light. So if you have a dark matter candidate to be of 1 GeV in mass, then its kinetic energy will be 1 keV. So, and this scale is much heavier than the atomic physics. It's much higher than atomic physics scale and much lower than nuclear physics scale. So it was a new region that was not fully explored before, and there's some opportunity there that one can sort of make contributions to neutrino and dark matter physics. It is a wide open field. Now let me start with a case study about why atomic physics can contribute to both fields. Let me start with the neutrino magnetic moment. So the experiment I have in mind is actually happening in Taiwan using reactant neutrinos. So you put a detector next to a reactor, and a typical neutrino energy scale is like 10 MeV or a few MeV. Then you look for an ionization process where the neutrino comes in and ionize the electron from the atom. And you can write down the complete set of structures, the form factors, to describe a neutrino properties. For example, this is the charge form factor, magnetic form factor, and the electric EDM form factor, and also there's a energy moment form factor. So this is a complete set. And then in the scattering process, let's start from the simplest one with the free electron. So you can write down the Feynman diagrams. Let's just consider the magnetic moment, so through the one photon exchange. Then for magnetic moment process, the helicity needs to be flipped. So there's a one insertion. So the chirality between the initial and final state will be different. But for standard model interactions, the helicity does not change, or chirality does not change. So this is an incoherent sum. And the cross-section for the free particle has some interesting structure. For the weak interaction, it is smooth in the energy transfer, T, we use T. And for the magnetic moment effect, it has a 1 over energy transfer. This 1 over T is coming from the propagated 1 over Q squared, because the kinematic constraint, T is proportional to Q squared. So you got 1 over Q squared behavior from the one photon exchange. And if the mini charge of the neutrino is non-zero, then you got 1 over Q to the 4th. So you got 1 over T squared behavior. It's even more singular. And so this is just the free electron case. What about in the realistic case that you've got a complicated atom like germanium? So experimentally, the Taxono group is using a germanium single crystal. And then there is a grand debate happening at PRL because Henry Wong's group, they argue that in this process, they think that it might be a good approximation to treat the photon as a free photon. They argue that if this is a good approximation, then the cross-section actually enhanced by 3 orders of magnitude. And the implication for experiment is huge because using the same set of data with this enhanced cross-section, they can have a much better constraint on neutrino magnetic moment. So without doing any more measurement, they automatically get much better constraint than all the others. But another PRL by W Chen company argued that no, this is not the case. They use sophisticated some rule argument saying that, well, actually a better approximation is to treat the electrons in the atom as free electrons. So which one is correct? As a theorist, we start from the simplest thing you can do by finding a toy model. And a toy model usually has to be fun to work with, otherwise it's not a toy. And also you have to learn something. And the model we identify is a hydrogen atom, where we can solve the problem exactly, and you can test various kind of approximations. And so I just skip the intermediate process, just tell you the conclusion. It turns out when the energy of neutrino, of the incoming neutrino is very small, then to treat photons as a real photon is a good approximation. Why a very high energy, you treat the electron to be free electron, that is a better approximation. It's actually easy to understand why this is the case, because when the neutrino energy is so high, it's much bigger than all the binding energy, binding momentum in the problem, then the binding effect should not be important. So at high energy, the neutrinos see the electrons as free electrons, so it makes sense, right? And at very low energy, the energy of momentum transfer is so small, so Q squared is take Q squared to be 0 is a good approximation. So we understand the 2 limits. And in terms of numerically, we see the transition happens for hydrogen atom to be 3 keV. Then this reminds you that this is nothing but the binding momentum of the hydrogen atom. So things works out. This is the scale that said that this is large scale that tells you about the binding effect. The binding energy is alpha times this one is much smaller. Okay. So we understand completely why certain approximation works in this toy model. But this is so this model is fun and informative, but it's not enough to settle the debate. So to settle the debate, we use a up initial calculation, which is a non-name MCRPA, multi-configuration relativistic random-based approximation. Let me explain briefly what that means. So we start from a Hartree-Fock wave function. That is saying that you convert a many-body problem into a single-body problem, saying that the electron is going to sit inside a effective mean field potential, and you solve the mean field potential self-consistently. Then you introduce particle-particle correlations. So the electrons can have 2-particle correlations. So you can have 2-particle, 2-hole excitations, for example. And then we want to put in the relativistic effect, because germanium has 32 electrons, and the expansion parameter is actually the z, the number of electrons times alpha. So that is not much smaller than 1 anymore. So relativistic effect needs to be put in. It's actually when it's using the derived equations, and but in this case, even the relativistic correction is important. The energy transfer is still not high enough to create particle and particle pairs. Then we also put in multiple configurations such that the initial state, since it's an open shell system, you have more complicated structures to start with. And then we just solve the equation. Start from an initial state wave function and put in the time variation of the potential which incorporates the electromagnetism, and automatically get the final state. So this is a benchmark result to test how well this machinery works. This is the photo absorption on germanium. Actually, this is a single germanium atom. And let me remind you that data is actually for a solid state. So you can see that when the energy transfer is about 0.1 keV, that is the threshold of the detector. The agreement with data is actually better than 5%. And at low energies, we think that now the solid effect is going to be important. So this is a nice demonstration that this method works. And then we look at the magnetic moment contribution. It turns out that it shows that it is quite the agreement with free electron approximation is actually quite good. And this is magnetic moment cross-section contribution, and this is the weak interaction. See that there is a 1/T behavior here. And this slide is just showing that even in the previous slide, we see the free electron approximation is very good. It's not always the case. When the neutrino energy is small enough, then the free electron approximation gives you the wrong phase space. So this is the plot for the complete set of electromagnetic properties. For this curve is for magnetic moment. We just put in the current upper bound for the magnetic moment and draw the curve. You can see it has a 1/T type of behavior, and this is from the mini charge. It has 1/T squared behavior. And this curve is coming from the neutrino nucleus coherent scattering. And you can see that if the detector threshold can go down to, say, 100 eV, then there's a chance to see the neutrino nucleus coherent scattering, which has never been seen before. So it says that actually experimentalists are quite close to this case already. And so by taking fit to data, there's actually some parameters that actually they are the best of the world. Now let's turn to the dark side. This is the constraint plot for direct dark matter detection in terms of unpolarized cross-section versus dark matter mass. And you can see that it has this kind of behavior with the best constraint to be between 1 to 10 GeV for the dark matter mass. And the constraint is worse if you go to higher or lower energy scales. And at this corner here, there's a neutrino floor background. It goes like this, and it's higher on the left. And one can easily see that why the best constraint is happening at a few GeV. The physics is actually coming from kinematics. If you think about it, when you play pool table, the billiard board game, then when you have two billiard boards, and one is at rest, and one is moving, then since their masses are identical, so you can actually transfer the kinetic energy from one board to the other 100%. Right? But if one board is much lighter than the other one, the energy transfer is not so efficient. And so that is why, because the nucleus has the mass of GeV times the number of nucleons in the system. So when this mass of the nucleus matches the mass of dark matter, you get the most efficient energy transfer. That's why the constraint is best at a few GeV range. And that tells you that there are a lot of opportunities at lower dark matter mass site, or light dark matter, and that's the region that we are going to contribute most. And also you can see that this is the constraint plot up to this February. After this summer, you see that the first bound is pushed down by Lux and Panda X. And you can see that they have comparable bounds from the two groups. And you can also see that the current bound is quite close to the neutrino floor. already. So how could we contribute? How could atomic physics contribute to dark matter detection? As I just mentioned, if we study the nuclear recoil, electron recoil, meaning that if we have a dark matter collide with an atom and kick out an electron, for this electron recoil event, the energy transfer is most efficient if the dark matter is closer to the electron mass rather than the nuclear mass. So the energy transfer is more efficient when the dark matter is light, so less than 1 GeV. Right? So we can compute the cross-section directly for germanium such that we can contribute to CDEX, and also for xenon, so we can contribute to xenon-type detectors like LUX, X, and LZ, which is a 7-ton detector that has been approved, and so on. And also, there is another type of background that we can also try to compute. That is some neutrino ionization or electron recoil from solar neutrinos. And why are those background to the dark matter detection? That is usually in okay. So if one is detecting not just the light dark matter but the typical dark matter, you look for nuclear recoil. And for this type of nuclear recoil experiment, if you have electron recoil, then there is a small chance that the electron recoil will be misidentified as nuclear recoil. And the chance could be quite small. Somebody argued that it's like 0.5% and could be even smaller. But even with this small chance, with the large solar neutrino flux and because the detector is so precise, this becomes an important background. And so it's important to compute those contributions. I will show you that why this is actually matters later on. And also, a third way we can contribute is that we can actually turn the xenon detectors as a neutrino detector, even without using additional radiative source. We just use solar neutrinos. And we can constrain the electromagnetic properties of neutrinos to quite high precision. I will show you why those are the cases very soon. So this is some electron recoil rate versus the energy transfer plot. And now I draw some two typical processes from dark matter detection. Say those are nuclear recoil signals from using two parameters. Those are two parameters close to or on the neutrino floor. And then this is the solar neutrino background, assuming that there is a. By the way, this is the plot made for Darwin using 30-ton. So this is a proposed study for the Darwin. The Darwin is using 30-ton of xenon neutrino, and the misidentification of a electron recoil to nuclear recoil is very small. It's only 2.2%. So using those parameters, you got this curve, by treating electrons to be free electrons. So this curve should be improved. And also there's a background generate another type of electron recoil that is coming from the 2 neutrino double beta decay. This could come from the materials of the detector. And so you can see that there's a window that actually those backgrounds are the highest. So that is the window that we hope that the background computation can be improved. So we set out to do the computation of neutrino xenon ionization, and this is the benchmark calculation using the photo absorption on xenon, so you can compare with data. And you see that the cross-section differs by 5 orders of magnitude, and our calculation agrees with data really well. If you do a more detailed comparison, this is the plus minus 5% error bar band. You can see that most of the region, the agreement is within 5%. With the less the agreement is not as good near the threshold region. But I was told by some experts that the experimental determination of those thresholds, the atomic thresholds, are actually not very precise. So, but the threshold region is actually quite small in the parameter space. So if you integrate from, say, from 2 keV and above, that this is the most crucial region for us, and do the integration, then we think the error bar is actually 2 to 3%. So this is our result, and the previous curve is just using free electrons, and then this is with the full ab initio calculation, and we assign the error bar to be 2 to 3% if we integrate over this region. And so this is kind of exciting because if we take a 17-ton-year exposure, and notice that the approved Darwin experiment is 7 tons. So if they measure 10 years, then they can actually give a constraint on solar PP neutrino flux with 1% statistical uncertainty. And so the constraint on this flux is going to be limited by theory, which we claim to be 2 to 3%. So this provides the opportunity to constrain low energy PP neutrino very precisely in a few percent level. And then let me just show this plot again. So this curve, those are the best constraints from various type of neutrino properties, and this is the weak interaction process. And so if this curve, that is just the PP curve that I just shown in the previous slide. So if we can measure this curve to be 2 to 3%, then imagine we can push the constraint on those, for example, mini charge and magnetic moment number to the improvement could be a few orders of magnitude better than the best constraints we have now. So this is just coming, just using the solar neutrino flux as the source. And so you can actually run the down-matter detection experiment and constrain those neutrino magnetic properties as a byproduct without having put a radial source next to the detector and ruin the down-matter detection experiment. So this is another interesting application. So let me summarize. Neutrino and down-matter particles are portals to new physics, and ab initio atomic tools are indispensable to study down-matter detector response with down-matter and neutrino background. And multi-ton liquid ion down-matter could become a very good solar neutrino detector to measure PP flux to a few percent accuracy and to constrain exotic electromagnetic properties of neutrinos with high precision. Thank you very much.
Okay, so we open for questions. So you support about the low energy scattering. You support Henry Lever result.
Yes. So we provide theory support for Tesono and the CDEX, also P9 and LZ, for example. All those are.
So then you get three orders, so like the better constraint on the type of momentum, or you know?
No, we disagree with their claim.
Oh.
So there is no enhancement in. So their approximation is not correct. So we have shown that by both the toy model calculation and the full calculation does not support their approximation. So it's the free electron approximation that works better.
Oh, okay.
So that debate is settled.
Yes.
I'm just curious about these neutrino detections.
Yes.
You said in the multi-tones, which you might not able to distinguish dark matter and the neutrinos.
Yes.
If you don't use directional information. Then you say actually these things can help you to identify neutrino.
Okay, so there are two things. First one is when you do a down-matter detection and use a nuclear recoil as a signal, then there could be some background coming from electron recoil, but you misidentify an electron recoil to be a nuclear recoil. And so there's only a small chance, like less than 1%, this could happen, but this is significant enough. The second thing is, if you don't take the electron recoil as a background, but as a signal, it turns out you can constrain certain neutrino flux or constrain neutrino properties. Yeah. So there are multiple implications.
Other question? Yes.
Yeah, so in terms of I mean, I guess for the dark matter case, one of the cases that you are very interested in is like axion-like particles, right?
Okay.
So I know that there are some other ideas or experiments being carried out where they are looking at, say, transitions in levels, either at the nucleus level or atomic level.
Okay.
Is this complementary? Is it more competitive? Any comments on that?
Yes. We can replace neutrino by axions.